All right, now we start to dig into the code to make binary codebook trees. And I want to look at how we can programmatically generate a codebook. So a dictionary whose key is a character and whose value is the binary code. And also how we can decode binary strings and go back to their original character strings. So let's first make the codebook. So I'll start the entry point as a method in the BCB tree class. I'll say get codebook. I should return, as I said, return a dictionary whose key is character and whose value is the binary string to use to encode that character. Okay. So I'll start the codebook out as the empty dictionary. I'll say, look, if this Huffman tree is not empty, then I can actually build it. Let's say self.root.build codebook. So I'm going to pass this along by reference and fill it in. I'm also going to pass along a list which keeps track of the bits that I've traversed so far, going left or right in this tree. So remember, when I go left, it's supposed to be 0. When I go right, it's a 1. So I'll have a stack, actually. Really a list, but I'm going to make it like a stack. That we'll push to it a 0 or a 1 depending on if we go left or right. So this is a lot like the way we've used stacks recursively in the past, including in the warping paths in assignment 3 when you were generating warping paths recursively. It's going to be very similar to that code. So I'll say now in the node class, that's where the actual recursion happens. I'll implement this method. So I'll say def build codebook. And as I said, it takes 2 parameters, the codebook, and also I'll call it bstr. So the codebook is that dictionary. So it's the dictionary of codebook we're filling in. And then the B string is a list of characters, which we can think of as all the characters we've traversed to get to this node, or really all the bits we've traversed to get to this node. All right, so now let's think what we need to do in here. So the first thing we can do is check to see, is this node that we're on a leaf node? So you remember, only the leaf nodes have labels associated to them, or keys associated to them. Internal nodes have a key of none. So what I can do is I can say if self.key. So if the key is not none, then this must be a leaf node, which means that we can complete the code for this key. Okay. So what I can say is codebook. So this key should be encoded as this bit string. So I'm just writing some Python syntax here, string characters together. So for example, the list 0, 0, 1 turns into just that string. Okay. So that's what that does, that join command. So what we're saying is we've gotten to a leaf node. Now we're ready to put an entry in our codebook for the character that's at the leaf node to be all the bits that we traverse to get there. Okay. Otherwise, if it's not a leaf node, then it's an internal node and it actually has 2 children. Always. And the reason is, this is by construction. If we go back and look at the pseudocode for constructing the tree using a deck, what we notice is, okay, the first nodes that we add are just all the leaf nodes with these characters. The internal nodes we add, we're always actually adding 2 children. So the tree will never have just a single child coming off of any node. You always have either 2 or none. Okay, so it's either going to be an internal node with 2 children or a leaf node. So in this case, I don't even have to check to see whether there's a left or right. I know that there is. So what I'll say is first I'll explore the left. So I'll say bstring.append 0, right? I'm going to the left, so I better put a 0 on there. And I'll say self.left.build codebook. Codebook, bstring. And then once I'm done, remember I gotta pop off and try something else. Okay, so now I'm gonna explore the right subtree. I'm gonna push on a 1. And do that recursively. And now I will pop. And that should be it. Once the recursion is done, I will have passed by reference what the codebook is. All right, so let's see how this works. So I made this tree here. Let's see if it gets the correct codebook. So let's run all this code. Whoops, I called this make BCB. All right, so there's the tree. The codebook is none. Why? Because I do actually have to return it when I'm done. Okay. So let's try that again. There we go. Okay, so let's see if this is right. So it says an I is 0, 0, 0, 0. Looks right. M is 0, 0, 0, 1. Let's just spot check a couple others. Z, 1, 1, 0, 0, 0. 1, 1, 0, 0, 0. There's my C. B, 1, 1, 0, 0, 1. I see that. J, 1, 1, 1, 1, 1. There it is. Okay. And here's a space. So a space is 1, 1, 1, 1, 0. Okay. Good. Looks like we were able to get our code, and it wasn't that much code to get the code. Okay. So now I just want to talk about how to decode, and you'll finish this exercise yourself. But if I'm given a string, so let's say that I'm given the string M, I don't know what I'm going to make, M, E, let's see, M-E-N-D, mend. So how do I decode this? So let's say I'm given this string. How do I figure out that that's actually mend? Well, okay, so I'm going to go 0, 0, 0, 1. I get my M. Okay. Then I go back to the root. And I go 1. I keep going until I get to the leaf. So 1, 0, 0, 0, 1. I get my E. Oops. All right. Now I go back to the roots. Every time I get to a leaf, I go back to a root. This is just something I can do in a for loop. Actually, I don't even need recursion. I can just walk through until I get to a leaf and then jump back up. Keep walking. So as soon as I get to a leaf, I have a new character I'm ready to make. So I got my M, I got my E. And now I'm back up here. I go 1, 0, 1, 1, 0. So 1, 0, 1, 1, 0. That's my N. And then I have 0, 1, 1, 0, 1, and I'm going to leaf. And now I'm done. So this is how far the for loop would go. So that's all you got to do to decode. It's not terrible. So give that a shot.